Okay, so thank you so much. I'm happy to be again in Erwin Schrödinger Institute and to have chance to present this rather general talk. Maybe I should say some words to explain how it arises. So I had some intention to organize some panel discussion on this topic, which is sometimes presented not fully correctly or even wrongly in the public. And but after all, a lot of qualified people apologized, so I had to. So in the meantime, I somehow just built this presentation by myself, and you may guess that I'm not actively working in these areas. If I'm a little working or just as a modeling in geophysics, so it's solid Earth, not atmosphere, hydrosphere. But on the other hand, I had some distant view, so it might be counted as some advantage. No, but yeah, some tolerance. But I discussed these topics, particular topics, with some experts. So during the time, so I think it developed, and I hope that you will. Well, I'm sure that everyone knows a lot of things about these topics, but anyhow, I hope that you will learn something at least little new. How to? Yeah, okay. So just for your orientation, the talk will have about 4 parts, which are to some extent related to each other, but only rather vaguely. So first I will present briefly some basic physics of atmosphere related to climate, and also the Schrödinger's idea about what is life. Then the role of carbon dioxide in atmosphere and how it influences the climate. Historically, in really geological scale, from Cambrium, let us say. And then contemporary anthropogenic carbon dioxide emissions in some political, social, economical context, and then some little forecast which I just played with. So let's begin. Basic physics. So as a closed thermodynamical system, one should count sun and planets, in this case Earth. Otherwise, Earth itself is an open thermodynamical system, which is important for life. So there is a big power coming from the sun on high temperatures. That means high energy photons. It's about 170,000 petawatt. 1/3 of this is immediately reflected. So this reflection is called albedo, but the 70% is processed deeper in the atmosphere and partly in the Earth's surface, and then come out. Basically, the same power comes out, even a little more, because there is also some geothermal power, about 47 terawatts, which is just 47 thousands of nuclear power stations. But anyhow, it's quite negligible in the overall balance. And it doesn't go so easily. So there is some transparency of the atmosphere, which is called opacity. And it goes in relatively cold temperature. That means low energy photons. Yeah, and okay, so altogether it's some sort of game between opacity and albedo. So between greenhouse gases, which are typically this carbon dioxide, this is just most famous one, methane, oxides of nitrogen, vapor, versus aerosols, which are oxides of sulfate and also fine particulate matter. and some others. So this goes against each other. And what is just some interesting topic. So Max Planck determines the energy of photons which are inversely proportional to wavelengths. I occasionally will mention Nobel Prizes for the particular people just to underline some importance of this sort of achievements. There is also Wilhelm Wien, German physicist, not living in Wien really, another Nobel Prize even earlier, who determined that the wavelength is inversely proportional to temperature. And incidentally, the ratio energy per temperature is constant, which means that the lower energy photons, there are about 20 times more, and they get out a big outflux of entropy. Of course, talking about entropy of single photons is not correct because it's a statistical quantity. So one must take it in some quotes. Some physicists wouldn't be happy with this interpretation. Well, I mentioned this geothermal power, so just let me spend a few seconds on this. So, so it is composed primarily from primordial heat, which comes back to the early stage of the planet Earth. This aeon is called Hadean or Hadeicum. So this is created, this arises from accretion from the solar disk and then differentiation, the core mantle structure. So this is about one half. The other half is radiogenic heat currently, so it slowly disappears. And it's particularly created by isotopes, which has half-time about 1 billion year. Because if it is shorter half-time, there are already not enough in the mantle. If there is longer, so they are basically stable and they also do not create any heat. So this is particularly thorium, uranium, these two main isotopes, and potassium-40, surprisingly. And it somehow disappears during time. And there is also some little contribution to tidal heating. So this is created particularly when moon orbits the Earth, and it creates some heat by some tidal forces, either through dissipation effects or just even without dissipation, it would heat. So coming back to opacity, so it is frequent. It depends on frequency and in a rather complicated way. So there are several holes, and one important hole is about half micrometer wavelengths, and the other is about 10 micrometers. And there are still some others. So, and particularly these two are important because it allows the high frequency photons to come in and low energy photons to come out. And the greenhouse gases just fill this hole about 10 microns. This is the problem. And of course, this tuning of Earth's atmosphere is vital for life in the Earth, because first it will play with entropy, and also it will prevent high energy radiation to come into the Earth. So particularly this gamma rays cannot come to the surface, which would be otherwise in conflict with single cell life. So another interesting physical aspect is that normally the heat is not trapped by the airs. Rather, more heat comes out than comes in, except some exceptional periods like now. So there is some just little disbalance, but not so much big. And some 90% of the heat is deposited in oceans. So they are slowly heated up, not much, but nevertheless. And here is some just from NASA graph. So now you see that the power, which is zeta joule per year, is little increasing. This zeta joule is some strange unit. So 1 zeta is 1000 exa, 1 exa is 1000 peta, 1 peta is 1000 tera, and tera is 1000 giga, and that already our standard world. Yeah. So, and just if you count the number of seconds per year, so you will come out to some more civilized units like 100 or 240 terajoules per second. That means terawatt, which is rather comparable with the geothermal power of the Earth. And most of this is trapped in oceans, some 10% in continents. So altogether, still more heat comes out from continents. So it's sometimes you can hear that the heat cannot go out from the Earth, and this is the reason why it heats up. So it's not exactly true. But what is true that the opacity somehow decays, or how it is now, simply the transparency is deteriorated by these greenhouse gases. So if you would like to transfer some amount of heat, you must make a bigger temperature difference. Temperature in the Earth is about 4 kelvins. You cannot do anything with it. So you cannot decrease it. So the only thing is that the temperature in the surface must be a little increased. So this is the mechanism. But it is not true that some substantial part of the heat cannot go out. So this would cause to melting of Earth within millions of years. So in some little larger scale, so you can see that the heat or the power which was deposited in ocean was zero up to mid of the 20th century, and only recently it started to grow. Yeah. So the role of entropy. Let's come to Erwin Schrödinger. We are in Schrödinger Institute. So this was his pioneering idea. He got a Nobel Prize already some 10 years before for this Schrödinger equation, which is on that memorial desk in the foyer of the University of Vienna, as you may notice. And his idea was that organisms lives on negative entropy, so-called negentropy. And that they must interact with environment, so it must be open system. And he also identified that what is essential are plants, photosynthesis, and this is the essence of and sunlight, and this is the essence of life in the planet. So just maybe to explain it a little, so you can imagine some stabilized ecosystem, some forest. If you come to this after 100 years, it will be more or less the same forest, but of course particular trees will be different. Some of them died, the other grew up. So altogether, if you just measure the weight, so the mass is still more or less the same. Energy, so chemical energy, electrochemical energy, potential energy, heat energy, again the same. So what changed? Because it was a living system. So a lot of processes comes during meantime. transport of mass, transport of energy, and all these processes in the sum produce entropy. So the entropy must be taken away. So this is Schrödinger's idea. Actually, this was some 6 years before. It was 75th anniversary of his booklet, What is Life? So this was some afternoon here in this institute. Here's the flyer. And so there are occasionally some articles about this, some more details, balance of energy. So you can see that there is some relatively big exchange between the Earth's surface and troposphere, so lower part of the atmosphere, which is due to this greenhouse effect. And you see that the troposphere is or the stratosphere, then it's relatively cold. So this is a big influx of entropy coming back. So this is what little deteriorates this negative entropy flux, which is essential for life. Yeah. So there are some other articles where these italic numbers refer to entropy radiation. So watt per meter square per Kelvin. So occasionally this issue is discussed really in a quantified way, and yeah. Okay, and it also depends how the entropy is proceeded in the Earth. So of course it would be different if it would be in plants, which is important for life, because this is the essence, photosynthesis. And then this is how this entropy is trapped. And then either we can eat it directly or through some fancy animal like cows or pigs. But anyhow, so this is just the circle of which makes life. So always photosynthesis is at the beginning. Or if this entropy is proceeded on deserts or glaciers, or some mere transport processes, because transport also makes produce entropy. So then it is not contributing to life, obviously. Yeah. And so this is some little part about some mathematics showing that even mere heat transport produce entropy, which is probably well known to the audience here. So just linear heat equation, Fourier law, so just parabolic equation. Mathematical test is usually by temperature, but this is not physically relevant. If you just test it by 1, means integration over space, I forget boundary conditions, you will come out to balance of internal energy, which is the first law of thermodynamics. If you test it by so-called coldness, which is inverse of temperature, you will see second law of thermodynamics, that means entropy balance. So one can just formulate everything from the single quantity free energy, again, quite known here. What is interesting that this basically the first choice of every engineer or computational physicist to take linear heat equation is not compatible with the third law of thermodynamics, because entropy at absolute zero should be bounded from below, typically calibrated to 0. So which means that the heat capacity shouldn't be constant, but should be 0 at temperature 0. So which is the third law is credited to Walter Nernst, so another Nobel Prize. Okay, so the second part. So CO2 from some geological time scale. Why CO2? So this was basically by definition articulated in so-called Kyoto Protocol in 1997, as a base gas for so-called global warming potential, and the other greenhouse gases are somehow just by agreement counted to this. So methane is counted with the weight of 300 approximately nowadays. It used to be a little less, and because it's difficult to compare it. Methane has much higher impact to greenhouse effect, but it has much faster extinction rate in atmosphere. So one cannot directly compare it. So this must be some agreement. So this is because sometimes people ask why just CO2, why not the others? Historically, the role of carbon dioxide, at that time called carbonic acid gas, was first identified by some amateur physicist or experimentalist, Ernest Foot, in the mid of 19th century. So this is the original article. So here you can see this carbonic acid gas. And then some decades later, so it was Svante Arrhenius who phenomenologically quantified the role. It was one of the first Nobel Prizes. And he also conjectured that it might have a positive effect to agriculture because in his time, so the emissions of carbon dioxide was very low, and just slow increase of temperature might be rather positive. He couldn't imagine that later it will be much faster. So, and of course, so he also said that industry would play a positive role in this respect. And he quantified that doubling of percentage of carbon dioxide will increase global temperature about 4 degrees. Just interestingly, so his far relative was or is Greta Thunberg, who somehow was confronted with this climate problems, and when she found, probably in her family, and when she found that nothing is going on, so then she got some psychiatric disease, so Asperger's syndrome, and stopped talking, and later she started talking again, and now I think she's talking too much even. So this is just interesting relation with Arrhenius. So this is some picture which I took from some report from Intergovernmental Panel of Climate Change. So I will still mention it several times later. And this is the somehow indirectly reconstructed concentration of carbon dioxide since end of Cretaceous era, 66 million years back. So you can. So this was when it was the extinction of non-flying dinosaurs, if you remember. So it was this impact to Yucatan area of some asteroid, and then volcanism. So then it was some little break, and then everything was relatively fast reconstructed in some only few millions of years. Temperature rises, tropic paradise, and just mammals started to dominate, and then they produce, I think also plants started to run, and they produce oxygen, and after all it cooled down the atmosphere because they absorbed carbon dioxide. I think this was the mechanism. So, and in the lower picture you can see rate of emission of carbon dioxide, And you can see, or sequestration, so you can see that it was nearly zero. You may have a look that this scale is particle per million per some time, and then on the left picture it is 10,000 years, then per century, and here per year. So you can see that we really accelerated very qualitatively the rate of emission of carbon dioxide in recent years. There are some prediction. This SSP means some strategies which was identified in Paris Agreement. This another number. So the strategies are from 1 to 5, and this representative concentration pathway is some radiation coefficient, which is little related with them. So you can see these oscillations in past 8,000 years. So I will talk about this a little later. So this is particularly taken from so-called EPICA project. And these scenarios are this IPCC. Okay, so this is how this concentration, so maybe I should still say that this ppm are units, particles per million, which means if you measure it here, so you would also measure something like 400 ppm. You have it, okay, good. Well, yeah, but this refers to average per year, which means there is some signal, seasonal signal. So in the summer it is different in winter, and this is different in southern hemisphere and northern hemisphere and in equatorial region. So these numbers should be taken. It should be really averaged all over the globe, all over the year, and then you will see such numbers. So this is concentration, and this is reconstructed temperature. So you can see that this was quite hot area in the early tertiary, and then it slowly start cooling down. And you can see that continents in early tertiary, early Eocene was little different. So but more or less how it is now, but you can see that Americas hasn't been connected, Africa was not connected with Europe, and so on. So in this scale, so it was still little movement of continents. Yeah, so, and you can see now the correlation, and note the forecast that if there is this Versist scenario, or Versist, simply just, I wouldn't classify it as Versist, maybe that it will be faster transition to just a tropic paradise. But it's a question whether it will be really paradise. So we will come back to the early tertiary with temperature. So it's really some interesting game which we are now playing. Yeah. So okay. So there is another scale still older, up to about 560 million years, which is where the fourth aeon started. Fourth aeon is called Phanerozoic, which refers to Greek words that life became visible. Because before it was rather single cell life in oceans, and so not much rapid. So you can see that it was also a big story in Paleozoic. So it was Cambrium, Ordovic, Silur, Devon, Carbon, Perm. Then Mesozoic was Trias, Jura, and Cretaceous. This is where reptiles dominated, and then mammals started to dominate. It has to be, it was also some ice ages. The most intensive was Cryogenian. This was in Precambrium, area where the whole globe was frozen basically up to equator for nearly 100 million years. Basically, the whole single cell life extinct at that time. There was some traces in some shelf seas and or in the deep ocean. And then some volcanism started again to ended the ice age, and then this Phanerozoic started. But even in the Phanerozoic, there has been a lot of various ice ages. There has been some extinctions. So, okay, I will come back to this later. And so then about in the late tertiary, this hominidae started to occur. So this is one of the Australopithecus, which populated the middle of Africa. This Australo means not Australia, but South Africa. This Lucy is reconstructed according to this fossil bones, and so there's been only a few bones, but they reconstructed it. It was found in 70s in Ethiopia, so now it is permanently in Addis Ababa. But it used to be last week still in Prague, first time in Europe. Yeah, and then you can see that the climate was cooled down slowly, and then all this hominidae has been under some evolutionary pressure, but some of them didn't extinct, so some the others did, and so Neanderthals, or there has been a lot of branches. But some of them adapted, and so then they survived a lot of glacial periods, interglacial periods, and only in the last interglacial periods, last 20,000 years, they started dominating, overpopulated the whole planet. That period is called Holocene, and recently this period is called Anthropocene because we have technological ability to influence some spheres. So atmosphere, cryosphere, hydrosphere, biosphere. So this is Anthropocene. Yeah. So this is the story of mankind, no? And you can see some extinctions. There's been identified about 19, but 5 of them had been really massive extinctions, mostly related with some cold areas, cold eras, but not always. It was some interaction with lithosphere also, because or crust, because it was sometimes very intensive volcanism which influences it. Sometimes it was related with impacts of asteroids. The last one, so this is this Cretaceous tertiary boundary in Perm, at the end of Perm. So this was the probably most massive extinction. And now there is a question whether we are at the beginning of the 6th mass extinction, but which is, if you just Google Wikipedia, you can read it there. But expert says that it is probably not beginning of the mass extinction. Surely not because of climate, rather because of direct activity of mankind. But it's difficult to compare because in 19th century a lot of species was heavily influenced by mankind activity, and now they are reconstructed. So it's difficult to say what is the real development. And okay, and here there is the relation between temperature and concentration since Devon, so it is not directly the same time scale. Maybe I will little jump it, and then that project EPICA, which I mentioned. So this is a European project for ice coring in Antarctica. So this was in years 96 up to 2005 in this area, which is called Dome Sea. This was parallel also some Soviet or later Russian project in Vostok area, which is little in some different spot. And Vostok ended coring a little earlier because I think this was, in one of the project it was already solid rock, and in the other it was some big lake which they didn't want to pollute. And after all, this European project traced back to 8,000 years back. Some isotopes investigation, so they can reconstruct both carbon dioxide in the atmosphere and temperature. And you can see that there was some 8 glacier periods and 9 interglacier periods recorded. Yeah. So the project ended at 05, and you can see that mostly the temperature was first, and then only carbon dioxide followed, but now it is rather different. So first carbon dioxide and temperature follows. And this is related with so-called Milankovitch cycles, or there is an agreement on this. I will just come back to this. So nowadays it's opposite, and nowadays it's also, we are in 430 ppm. So this is the picture from when the project was ended. This Milankovitch cycle, so it refers to orbiting Earth around Sun. And there are some periodic influence, basically from Jupiter and from Saturn. So there are 3 aspects: eccentricity, obliquity, and precession, and they somehow are in resonance or in interact with each other. And this is what influences this ice, this glacier and interglacier periods. Milankovitch was Milutin Milankovitch was a Serbian physicist. And and what is also interesting that in the mid of Pleistocene, about 1 million years back, or 1,200,000 years, 100,000 years back, so this was there was some transient from period about 41,000 years to 100,000 years. So now we are in some interglacier period, which now lasts about 20,000 years, and still after another 80,000 years there will be the next interglacier period. And in the meantime, the climate should be cooled down if we wouldn't do anything. But we are now doing something, some warming, so it's question whether we will cancel this Milankovitch cycling or not. So I think there is not a general agreement on the future development. And now there is another drilling which should be on some different spot, which should trace even longer period before this mid-Pleistocene transition. But still this project is ongoing. And 1 year after this EPICA project ended, it was some movie professionally produced by Paramount, full-time movie. Al Gore was the scenarist and also the main actor. So this was the first time when there was a lot of various aspects, sometimes presented not in a correct way, but among them, so first result of this, the first public release of this EPICA project was then. So you can see this graphs, this 8 ice glacier periods and 9 interglacial periods. Al Gore is on some telescopical plateau, and you can see that, so this is just movie, that he presented the prediction for the future, and he is now on the top. So this was really shocking of a lot of people. And 1 year after, so the director got an Oscar for best Oscar award for best documentary movie, and Al Gore got one half of Nobel Peace Prize, shared with this IPCC, which was that time running about 18 years. And it's a permanent platform, so it is still running, of course. And this is some picture which reflects at that time already Google existed, so some activity on Google as far as this climate words. So Al Gore, you can see it clearly visible, and also later Greta. Greta was a small child when Al Gore launched this movie. And in the meantime, there's been, of course, a lot of other activities, and let me mention the second encyclic of Holy Father Franciscus, which is maybe not generally known, but particularly I think about among Catholics it is known. And this is really very interesting encyclic, about 100 pages, and minimally half of this is devoted to climate, to pollution, water pollution, loss of biodiversity, anthropocentrism, critics of anthropocentrism, adoration of science. So really just very surprisingly, very professionally written, tens of pages. Very ultimate, and it influences Paris Climatic Agreement, which happened about 6 months later. So I think it was just released in a good time for papers. So this is another graph. And in the meantime, there's been, of course, a lot of other activities in the pre-Google area, I would say. So this was one milestone, was the book by some scientist and writer Rachel Carson about, so this was called Silent Spring, and she pointed out the really bad impact of DDT. This is trichlor something, which was, so this is anti-insect agent discovered by Miller was his name in 1939. Then it saved a lot of American lives, and also some lives in concentration camps after the end of the war. So American lives in Pacific at the end of the war. And Miller got a Nobel Prize for this in 1948. But then it occurred that it's rather devil's invention, and then Rachel Carson somehow make it explicit, and then later it was it is some initiative not to use it, and now it is basically not used except in Africa somewhere. And then it also directly initiated the creation of United States Environmental Protection Agency. This was, I think, during Bill Clinton time, or maybe Nixon. And maybe you know this from, I think, 10 years ago. This was this Dieselgate. So this is this agency. It started with some 6,000 or 7,000 people. Now it has some 17,000, which is what Donald Trump says, and he intends to cut the budget by 2/3. So also this was Club of Rome, so the famous book Limits of Growth, United Nations Environmental Programme. So this is again some permanent platform from that time, the World Environment Day is every year in June 5, and so a lot of initiative in the meantime. Okay, the third part, temporary anthropogenic CO2. So this is some graph which you can get from this web page. You can play with it also somehow, as far as time scale and selection of. So I try to identify some economical and social economical context. So one can see the second industrial revolution. So then some plateau in the big war, some local maximum when exactly in 1929 when there was a New York stock market crash, then some decay until 33. This is when in Germany, Nazi came into power, in Japan, so it was also a big initiative to Manchuria. In the meantime, also Ethiopia, invaded by Italians, a lot of concrete construction, so Siegfried Linien, then Czechoslovakia reinforced highways, and so because concrete is just a big source of CO2 emissions, steel factories, and so you can see that it started to rise. There was some break in 35 approximately, so this was visible even before. So from 35, I have a separate picture. So you can see the end of, I would call it 30-year World War. And then it goes basically straight. So this is not cumulative emission. This is rate of emission. So on that page, if you see 40 billion tons, it first means American billions, so our milliard. So it is gigaton, but per year. So you can see that the rate is still constantly rising. So Kyoto Protocol, nothing. It was 97, but in effect it was several years later because some states block it, particularly Russians. Not surprising. So recession, nothing. Maybe Paris Climatic Agreement little slow it down. So it's too early to see it now, but it might be some. But anyhow, so it is still rising. So this is just by states. So you can see that China starts dominating. So not surprising, it is ever discussed. You can also see that in America, in the United States, maybe Al Gore movie had some influence. There was also some economical crisis in that time, but nevertheless, it seems that it's some constant trend to reduce emissions. So up to now, but now it's not clear that the new president, old new president, may reverse the trend. So India is rising, European Union, so this is just projected back because before European Union doesn't exist in the scale 27 states. So realize it. But the European Union is a little decaying. You see France, Austria, Germany, so still rather small portion. Nevertheless, if you see it on per person, so it's different picture. So Germany is still above European Union average, Austria as well. And China is basically comparable with us. So Czechia is, if I forget Luxembourg, which is small really, so then we are the first. Unfortunately. So although we are constantly decaying because we had really very big industry, so it's not so difficult to decay, but nevertheless. No. And now we are comparable with China, but China is still rising. No. Yeah, okay. And then the last part, so some little forecast, short time forecast, several decades, let us say, for the future. So this was that I somehow try to understand what these numbers mean, which are spoken often in public. And after all, it was not so easy for me to realize it. So I will briefly present it. So I just played with a single linear ODE. So you cannot imagine anything simpler, which is actually sometimes used for dynamic of some other greenhouse gases like methane and for carbon dioxide, it's really quite big simplification because the dynamic of sequestration of carbon dioxide is more complicated than the others. So one should realize that it is rather only short time prediction. So there is this coefficient RSE is sequestration rate, which is not explicitly seen in literature. So I try to identify it. And REM is emission rate. So this is basically what one can read from the pictures which I presented. And some initial condition, which also should be somehow read from literature. But it's not so easy because in literature you see concentrations in ppm and emissions are in mass, in gigatons. So one must somehow recalculate it. So for this, one should realize the total mass of the Earth's atmosphere, which is just this 5 times 10 power 18 kilograms. This is what Wikipedia says. And then one should, because this ppm is molar concentration, so one should realize what is the molar weight of carbon dioxide composed from dominant isotopes, carbon 12, oxygen 16. Then the resting atmosphere is basically molecules of nitrogen, molecules of oxygen. Of course, there is some argon, there is ozone, and so on. And this is 80% nitrogen, 20 oxygen. So, and this gives some coefficient 1.5, which later I found even on some Google. So this is a correct number. And then pre-industrial concentration was 280 ppm, which corresponds to what 2,200 gigatons in the atmosphere. And in 1935, it was 300, so which means that there was some extra content, which was 150 gigatons. So this is the initial condition. And then this year, we have 430, which means some extra anthropogenic content, about 1,100 gigatons. So I would like to fit these numbers. And also this emission rate. So in 1935, it was, so this was some land use rate, which was basically nearly constant. So 5 gigatons per year. And then in 35, the industrial emission was about 4 gigatons years. Nowadays, so altogether 9, and nowadays it's about 40 gigatons per year. And it's still rising. So 340 megatons per year square. So this is acceleration. So we are still rising the rate. So this is what should be put into the model. Also, one information is important, that we can really take as a base the whole atmosphere, because this is what I consulted with some physicists who work in atmosphere, that basically carbon dioxide is well mixed, surely throughout the whole troposphere and even through whole stratosphere and mesosphere, which contains basically the whole atmosphere, what is above in thermosphere and so on. So it's very diluted, so one can forget it. Which is quite surprising, because carbon dioxide is 1.5 heavier than the rest of the atmosphere. So one should expect that it will be rather in the ground and not mixed, but reportedly it is mixed. So this is also one information one should take into account. And then I will try to identify the sequestration rate, and it comes out that the correct number is about 2.5% a year as a sequestration. 1.5 would be too less, and 3.5 would be too much. So I think. Okay, so having this number, okay, so this 2.5% corresponds to a half-time of extinction about 26 years, which is maybe rather optimistic, but this is because there are several sequestration mechanisms, and some part of this really lasts in the atmosphere hundreds of years or even thousands of years. But the other part is sequestrated relatively fast. And also there must be some evolution. This is what some literature emphasized. So this is really quite difficult how to forecast it. So this is some picture from some, I think, quite well-cited publication, which suggests that one should take not a linear ODE, but rather some nonlinear ODE or some integral equation. So this should be surely much better model. So one should take in mind that this single linear ODE is very simplified and is valid for just relatively only a few decades maximally. Okay, so I took it and played with it. So there are some 3 scenarios more or less according to this Paris Agreement, SSP 1, 2, and 4, which corresponds roughly to some pictures which you can see in this IPCC reports. So then it is, if it would be implemented in the year of Paris Climate Agreement. Now we are, however, a little farther. So this is how, if it were implemented just this year, which will not happen, but okay. So I put this rate into the model, and the first experiment come to these 3 scenarios. So this is how the carbon dioxide would evolve in the future up to the end of this century. And this is the years from 1935. The second scenario would be this one. Yeah? So SP would be if we would frozen the emissions to 40 gigatons per year, which doesn't seem that it will happen. And if I compare it with Arrhenius, so this is what is now called the mid-term equilibrium climate sensitivity. So every doubling of carbon dioxide content would lead to 4 degrees. So you can see that at the end of century, the worst scenario would be 4 degrees global warming. In that 6th report of IPCC, it is mentioned that it might be between 2 and 5 with a 9% chance or even more. The previous report, which was launched some 8 years before, it was a little lower forecast, little lower chance. So they are improving the forecast, and it seems that it will be still worse and worse. And in this 6th report, it is mentioned that some new generation model has even some worse forecast. And also one should realize that from 2 to 5 Celsius increase of temperature compared to pre-industrial time means the global warming. One should realize that northern hemisphere is warmed faster than southern hemisphere, and continents are warmed faster. So if we do not stop the Gulf Stream, so then we may expect rather some 4 to 10 degrees at the end of the century in the worst scenario, which probably will not happen. So it will be something in between. Yeah, okay, some questions to the end. So I will not answer it, it's just questions to everyone. Whether there is politically feasible option to have some scenario which is better than this versus one, which is business as usual. This is, this is complicated game. This is in our language. It is multi-criteria, non-cooperative game. Players might be either states or some industrial corporations. Strategy is either Green Deal or some influence of journalists, and criteria is maximize gross domestic product or maximize profits of the corporations versus some minimizing of the world emissions. So this is what links it, what couples it together. And so from this you can imagine that it's a very complicated structure of some non-cooperative multiplier game. And so it's difficult to imagine that some strategies will be really optimal in whatever sense. Yeah. So if the warming will be really accomplished, because now it's just ongoing and maybe starting. So what political geopolitical consequences will it have? So some civilizations may disappear, particularly Western civilization, I think, with this over bureaucracy has time maybe 200 years maximum. And important question is whether we will see some substantial loss of biodiversity due to this warming, or maybe even in some next century, some mass extinction events. Or it might be opposite, that higher carbon dioxide, higher temperatures sometimes may lead to just bigger growth of plants and also ecosystems, animal ecosystems. And of course, some species will, or basically all of them will be under big evolutionary pressure because the change is relatively fast, which might not be bad. Some of them may adapt and may develop some even better forms. The other will extinct. Okay, so this is what I already mentioned. Another question is whether the entropy budget, which I mentioned before, is really might play some important impact on the climate and on the life. So there is some agreement that maybe we are, some conjecture that we are probably far from the borderlines. So maybe the entropy and that Schrödinger idea is maybe not so essential for this climate and for the life as it is now. And this might be reflected that there is not a single word about this IPCC reports, and some of them has more than 2,000 pages. Simply no single word about entropy, although in literature you can find relatively a lot of articles about this. And the last question is, what message can we take from all that knowledge which we have and which we will have at our disposal? What goals should it be? So should we really stop the emissions very markedly, which might be maybe not bad, because it might be good to have these fossil deposits to be used later when the climate will start cooling to the next glacial period. So then maybe we can compensate it. But now we are burning it and we will not have it. Now they will remain in the atmosphere maybe some 2,000 years, but maybe we will need it for another 20,000 years when the climate will really start cooling. Who knows? So, and whatever we did, so this is just some old Jewish quote that when we plan something, so this is what makes God laughing. And okay, I took my time, so thank you very much for your attention.